The topic of this lecture is solved examples of improper integral. We'll cover example number 1, example number 2, example number 3 and example number 4 in this lecture. So let us see example number 1. Here we have to show that improper integral 0 to 1 dx upon x plus 1 into x plus 2 into under root x into 1 minus x is convergent. That we have to show. So let us see the solution. Let the given integral is I is equal to 0 to 1 fx dx. That is, we are supposing this integrand as a fx. Now clearly the x is equal to 0 and x is equal to 1 are the only point of infinite discontinuity of fx. Also, fx is greater than 0 for all x belongs to 0 and 1 in open interval 0 to 1. So this is very clear. Now we'll examine the convergence of improper integral 0 to 1 by 2 fx dx and 1 by 2 to 1 fx dx. That is, the interval 0 to 1 we have divided into two parts, 0 to 1 by 2 and 1 by 2 to 1, and we'll see whether these two are convergent. So let us check the convergence of 0 to 1 by 2 fx dx at x is equal to 0. For this, we take mu is equal to 1 by 2 and we find the limit x tends to 0 plus under root x into fx. And we get limit x tends to 0, 1 upon x plus 1, x plus 2 under root 1 minus x. And when we put x is equal to 0 here, we get the value 1 by 2, which is a finite non-zero quantity. Now here mu is less than 1 because mu is 1 by 2. So by mu test, we conclude that 0 to 1 by 2 fx dx is convergent. Now let us check the convergence of 1 by 2 to 1 fx dx at x is equal to 1. Here also we take mu is equal to 1 by 2 and we find the limit x tends to 1 minus under root 1 minus x into fx. And we find that we obtain limit x tends to 1 minus 1 upon x plus 1 into x plus 2 into under root x, which is equal to 1 by 6, which is again a finite non-zero quantity. Again here the value of mu is less than 1 because we have supposed that mu is equal to 1 by 2. So by mu test 1 by 2 to 1 fx dx is convergent. Now because this is convergent and this is convergent, both these are convergent, so we conclude that 0 to 1 fx dx is convergent. Now let us see example number 2. Examine the convergence of 0 to 1 x to the power p minus 1 upon 1 minus x dx. Now solution, clearly 1 is the point of infinite discontinuity of integrand, this integrand, and also if p is minus 1 is less than 0, that is p is less than 1, then 0 is also a point of infinite discontinuity. From this it is clear that if p minus 1 is less than 0, so this comes down and 0 is also become the point of infinite discontinuity. So again we'll break the interval 0 to 1 between two parts as a 0 to 1 by 2 and 1 by 2 to 1, and we examine the convergence of integral 0 to 1 by 2 x to the power p minus 1 upon 1 minus x dx and 1 by 2 to 1 x to the power p minus 1 upon 1 minus x dx. So step number 1, convergence at 0 when p is less than 1, that is, this is the condition. Let us suppose that fx is equal to x to the power p minus 1 upon 1 minus x, and we suppose gx function as a x to the power p minus 1 when x belongs to this interval. Then clearly the fx is greater than 0 and gx is greater than 0 on this interval, and when we find the limit x tends to 0 plus fx by gx, we get limit x tends to 0 plus 1 upon 1 minus x, which is equal to 1, a non-zero finite number. Therefore, fx and gx converges or diverges together. Now let us examine the convergence of gx. So 0 to 1 by 2 gx dx, which is 0 to 1 by 2 x to the power p minus 1, which can be written as 0 to 1 by 2 1 upon x to the power 1 minus p dx. This is convergence if and only if 1 minus p is less than 1. Because here mu we can suppose as a 1 minus p, and we have previously seen that if the value of mu is less than 1, then this type of improper integral is convergent. But 1 minus p is less than 1 is equivalent to p is greater than 0. So it follows by comparison test, because now gx this is convergent, so it follows by comparison test that 0 to 1 by 2 fx dx is, which is equal to 0 to 1 by 2 x to the power p minus 1 upon 1 minus x dx is converges if p is greater than 0, and it diverges when p is less than or equal to 0. Now let us see the step number 2. Here we'll check the convergence of 1 by 2 to 1 x to the power p minus 1 upon 1 minus x dx at x is equal to 1. So let us suppose fx is equal to this function, and gx now we'll suppose as a 1 upon 1 minus x. So clearly for all x lies in this interval, fx is greater than 0 and gx is greater than 0. Now we'll compute the limit. Limit extends to 1 minus fx by gx, and when we put x is equal to 1 over here, we get the value 1, which is a non-zero finite number. Therefore, fx and gx converges or diverges together. Now 1 by 2 1 upon 1 minus x dx, that is this is gx. So this is 1 by 2 to 1 gx dx is convergent. Why this is convergent? Because when we compute this using the definition, so it is limit extends to 1 minus, and this integration is minus log 1 minus x, and when we put this limit, and finally when we put limit epsilon tends to 1, in this expression we get the value log 1 by 2, which is a finite non-zero number. Hence this integration is convergent. So 1 by 2 to 1 x to the power p minus 1 upon 1 minus dx is also convergent. So because both the integration is convergent, so we conclude that 0 to 1 x to the power p minus 1 upon 1 minus x is convergent. Now let us see example number 3. Here we have to show that integration 0 to 1 x to the power m minus 1 into 1 minus x to the power n minus 1 dx is convergent if and only if m and n are both positive. That we have to show. So let us see the solution. Let the given integral is 0 to 1 fx dx. So this we have considered as a fx. Now it is proper when m is greater than 1 and n is greater than 1. This is very clear from this expression. Now step number 1, x is equal to 0 is point of infinite discontinuity of fx is m is less than 1. So it is clear, if m is less than 1, then this goes down and x is equal to 0 becomes point of infinite discontinuity. Similarly, x is equal to 1 is point of infinite discontinuity if n is less than 1. Now we will examine this interval 0 to 1. We will divide again into two parts, 0 to 1 by 2 and 1 by 2 to 1. So we will examine the convergence of 0 to 1 by 2 x to the power m minus 1 into 1 minus x to the power n minus 1 dx when m is less than 1, and convergence of 1 by 2 to 1 x to the power m minus 1 into 1 minus x to the power n minus 1 dx when n is less than 1. Now let us see the convergence of this integral at x is equal to 0 when m is less than 1. So clearly the fx is greater than 0 for all x belongs to this interval. 0 to it should be 1 by 2. Now limit x tends to 0 plus fx into x minus 0 to the power 1 minus m, which is x tends to 0 plus 1 minus x to the power n minus 1. And when we put x is equal to 0, we get 1, which is a finite non-zero number. So therefore, by mu test, the integration 0 to 1 by 2 fx dx is convergent if and only if this 1 minus m, which we are considering here as a mu, which is less than 1. That is, when we solve this, we get if and only if m is greater than 0. Now let us check the convergence of this integral at when n is less than 1. So again, clearly here fx is greater than 0 when x lies in this interval, and when we find limit x tends to 1 minus fx into 1 minus x to the power n minus 1, and when we calculate this limit, we get 1, which is not written over here, but it should be 1, which is a, this limit is 1, which is a finite non-zero number. Thus, by mu test, 1 by 2 to 1 fx dx is convergent if and only if 1 minus n is less than 1. Because here this 1 minus n, this 1 minus n we have considered as a mu. So if mu, value of mu, that is 1 minus n, is less than 1, so this is convergent. But 1 minus n is less than 1 is same as n is greater than 0. Therefore, both the integral, this integral and this integral are convergent if and only if m is greater than 0 and n is greater than 0. Hence, we conclude that integration 0 to 1 x to the power m minus 1 into 1 minus x to the power n minus 1 dx is convergent if and only if m is greater than 0 and n is greater than 0. Now remark, the integration which we have discussed in the previous example is called a beta function, and it is denoted by b in bracket m comma n. Now let us see the fourth example. Here, show that 0 to pi by 2 x to the power m upon sine to the power n x dx is convergent if and only if n is less than 1 plus m. Now let us suppose that given integration is I, which is 0 to pi by 2 fx dx, which can be written as x to the power m minus n into x upon sine x to the power n dx. Now let us see case number 1. If m minus n is greater than equal to 0, the integral is proper. Why this is proper? Because limit x tends to 0 plus x upon sine x to the power n is equal to 1 in this case. So this integration is proper in this case. There is no problem at all. Now let us see case number 2 when m minus n is less than 0. In this case, 0 is the only point of infinite discontinuity. From this is very clear. Now again, since fx is greater than 0 for all x belongs to this interval, so we take mu is equal to n minus m, and we find the limit x tends to 0 plus this limit, and when we calculate this limit and we find this limit, we get the value 1, which is a finite non-zero number. Therefore, by mu test 0 to pi by 2 fx dx is convergent if and only if m minus 1, m minus n is less than 1. This is mu here, which is less than 1. That is, if from this we get that n is less than 1 minus m, from this we get this. Thus, the given integral is convergent if and only if n is less than 1 plus m. So thank you very much. You can find this PPT in the description as a link. Thank you.